folks, and welcome to this tutorial on producing advanced higher level data tables and graphs on spreadsheets. I'll be using Google Sheets today because it is available to everyone and you can access it on pretty much any device nowadays, but everything I'm doing today can also be done in Excel. I'm going to be using just a random set of Pendulum data because it allows me to show you all the different sorts of manipulations that you'll probably need to be able to do all the way through your advanced higher course. I'll link the data below so that if you want to copy and paste it into a sheet of your own and do it along with this tutorial, you can. I'd really recommend that because this is a pretty dry subject to just watch the video. So I'd really recommend doing the tutorial alongside me. So I'm just popping in my length label here, and immediately we run into a problem where we can't put in the plus or minus for the reading uncertainty. So the way I get around that is to do special characters in Google Sheets. I open up a Google Doc in another tab and insert the special character in that Google Doc. So I have one just saved to demonstrate here, but you just open a blank Google Doc and go up to Insert, Special Character. Now I have my screen here on about half speed, so that's why my mouse seems to float over things for long periods of time. So insert special characters, and it has this draw function which I find brilliant, so you can just draw a vaguely close representation of the thing that you want. And if you float your mouse over each one, it'll tell you what you're looking at. A lot of these look the same, but actually only one of them is the mathematical plus or minus symbol. And there it is. So I click it and it appears in my doc. I go and highlight it, Control C for copy. I head back over to my sheets and I paste it into the cell. And then I have a good think about the reading uncertainty for this. So this is the length of a pendulum. It's a classically difficult thing to record. Difficult to know when to start your length measurement because you've got that odd connection with your pivot point. And then it's difficult to know where to end your measurement because you should be ending your measurement at the centre of mass of your bob, which can be a difficult place to locate. You've often got a floating measurement, so you're often holding your ruler or meter stick up next to your hanging pendulum, which makes your measurement inherently inaccurate. So there's loads of things going on here that make these length measurements quite poor and lead to systematic uncertainty. So I'm having a think. You can see me processing my thoughts about how big or small I'm going to make my reading uncertainty. I'm trying to imagine myself actually taking the readings, so I've taken this data from somewhere else. So at first I say plus or minus 1 millimetre. 1,000th of a metre there you can see, and then I will go back and I will change that because I think there's no way anyone really measures the length of their pendulum to within a millimetre's accuracy. So I go back and I change that to half a centimetre, so 5 millimetres, which I think is still being pretty generous to the measure. I think when you're measuring floating measurements like pendulums, where it's very much up for argument where the measurement should start and end when you're taking it, I think increasing your reading uncertainty is only being a better scientist. So, you know, we could be out by a centimetre there. I think that's perfectly reasonable, but I've put half a centimetre as my reading uncertainty for this one. So now I'm going to do one of those nice little spreadsheet tricks that you should know. If I pop my mouse at the edge of the column like that, where that double arrow appears, and double click, the column will automatically resize itself to be the perfect width for whatever I've written into that. So you'll see me using that a number of times today, and particularly at the end. This table is going to look very big when we're putting it together. We've got a lot going in here, and I'm a very big fan of having absolutely everything in your data table. So so it's going to look very big, but using that double click, so popping your mouse at the edge of at one side of the column, the little double arrow will appear. You have to do it at the top of the column where the letters are A, B, C, D, and double click. Resizing it to its natural width is fantastic, and also makes your graph a lot more tidy looking and actually a lot smaller in the end. So now I've got my reading uncertainty for my length, but in advanced higher I have two other uncertainties at least to take care of here. I've got the calibration uncertainty in that measurement. I'm not going to repeat my length measurements, but I now have a reading uncertainty and a calibration uncertainty, so I will have to combine those two into an overall delta L, an uncertainty in my length. So I'm going to be putting in another special character here for the delta C and delta L. So again, I'm going to go back over to my, my Google Doc to go and get those special characters. So I hope you're doing this along with me. Remember, of course, just pause the video at any time to keep up. Got myself into trouble there. Start again. So you can see I've already really found it on this one. But if I go and hover over, it will tell me which one is the appropriate actual symbol for delta. There it is. Select, highlight, Control C, and back over to my spreadsheet, Control V into my cell. So apologies there, I'd forgotten to bring my tab back to my spreadsheet, but here you can see I've just pasted in delta for delta C and delta L, and just drag them below my overall title there. We'll tidy that up in a second. So now we're going to start popping in the period information. So this was my dependent variable, as the period of pendulum varies with the length of pendulum. So capital T for period in seconds. Again, I'm going to paste in my plus and minus symbol for my reading uncertainty. Now that I've got plus or minus and delta in the spreadsheet, I no longer have to go back over to my doc to get it. I can literally just copy it from any previous cell. And remember guys, you know your reading uncertainty for any digital measurement the second you look at your measurements. It is the smallest digit you could have made with however many decimal places your measuring device is giving you. So I had some weird formatting quirk going on here, but there we go, plus or minus 0.01 seconds. And this is now where my repeats will go. So underneath that big title, we will now have our 5 repeats, which is our advanced tire minimum. Like I say, we usually recommend 6, just to overcompensate. But 5 is your advanced tire minimum, 5 repeats and 5 individual sets of data. I would normally say though, to make a reliable line of best fit, your minimum sets of data should really be 8 to 10. So our mean, I'll paste in a delta for random uncertainty, which goes immediately after your mean. But I am about to make a mistake here where I put in my delta C column and carry on from there. Don't worry, I do catch it later on and I pop in a delta U column. I think it's just because I'm looking at my previous column and just kind of copying that format, so I put delta C in first. So we'll come back and catch our random uncertainty once we finish setting up our table. So I'm not going to populate it until I've kind of sorted out and set out my columns. Of course, you don't have to do it this way. I'm trying to show you like a full and complete data table here, but it would be quite natural for you to populate it kind of as you went along if you were carrying out this experiment from scratch. So ultimately we will have our reading uncertainty, our random uncertainty and our calibration uncertainty in the period, and they will all be combined into an overall uncertainty in the period delta T. Now I'm going to go back and start formatting this to make it look much more like a table. So first of all, I've got this length title, and that's going to cover my length measurements, their calibration uncertainties and the overall uncertainty in length. So I'm going to highlight all the boxes that length covers, and I'm going to use this merge cell button right there and then ask it to sit in the middle, and that will allow me to have a length title that covers all of those 3 columns where the length information is. What's really important about this is that length in meters, that unit of meters, covers all 3 of those columns. So that is one of the main ways that people lose marks in their data tables, is that they don't make their unit title cover all of the columns that that unit is supposed to apply to. So my unit of meters applies to the measurement length, the actual measurement, the calibration uncertainty and the uncertainty in L. So it's really important that I merge those cells at the top and get length to cover all of those boxes. So now I'm just going to put an overall box around my length column, and I'm going to do the same here for period. So I'm going to highlight all of the distance that seconds unit covers. So all of those repeats, the mean, calibration and delta t, merge cells, ask them to sit in the middle. Okay, that merge button is just beside the boundaries, the borders button. And again, I'm going to put a big border around all of period. Now, I'm not a fan of excessive borders. I don't particularly like lines in between every single number. I actually find it as a marker, it makes it harder for me to follow lines of data. So I'm going to show you what I think is the ideal amount of borders, etc., to make something look good and professional. I have seen more, I have seen less. I think fewer borders than this is probably starting to get confusing because you're not dividing up your data. So I'm not going to put a line in between every single one of the repeats. I'm going to put a line between my 5 repeats and my mean, being very careful not to separate the mean from my overall period title and units there. So the line between repeats and mean stops before I get to that title at the top. And then they're all coming under the same units. There we go. So I'm not dividing, those lines do not go divide up and separate between my titles. Same here, my delta C and my delta L all come under the length in meters title. And divide those columns as well. So I hope you have a table looking pretty much like this now. This would be a good opportunity to pause and get your table up to this point before we go any further. But we're going to start thinking about processing our data now. So for the simple pendulum formula, there's some square roots going on, there's a 4 pi constant. So we rearrange that and do some analysis to know what we're gonna plot. But what we're actually going to plot to see our straight line is t squared and 4 pi squared L. Now t squared is something really tough to get into Google Sheets, something to a power. I don't know why they've made it so tough. But something to a power is really hard to type into your cell. So this is my workaround. I will paste this Google Sheet into the description of this video. Some wonderful person on the internet has made these copy and pastable cells of superscript and subscript numbers. So all you do is copy the cell and paste it into your own sheet. There are other more complex ways of getting powers into your sheets. You can use char codes, for example, but it's really not worth it at this level. So copy and paste this cell. Once you have this cell pasted into any one of your Google Sheets, you can of course then use it for anything else. You then just double click on the cell, you replace the X with whatever it is that you want to put to a power. So for us it's capital T, and then just delete all the superscript and subscript numbers that you're not interested in here. So for me, that's just deleting the 0 and the 1, and then every number after the 2. And there you have the value t squared, and you can take bold off it, you can change the size of it, you can copy and paste it all around your spreadsheet, and that's it, done. We also, of course, if we're doing t squared, want to have the units seconds squared, so I'm just going to pasting that thing again, replacing the x with small s, and deleting all the superscript and subscript numbers I don't need. Unfortunately, this is not a fix for superscript or subscript letters, and I don't have an easy one for you for those. I will say, however, though, that markers are very aware of the issues with getting superscript and subscript into sheets, and they will not penalise you for not being able to get your formatting perfect. However, if it's squared numbers or subscript numbers, we really should get them in. So this is a way of doing it. But with letters, I wouldn't worry about it too much if you really can't achieve it. So I'm just changing the size there because the paste in was a different size to the rest of my sheet. But that makes me think I actually probably want to make my titles a little bit more stand out. So I'm increasing their size and making them all bold. And I'll do the same for my subtitles. I'm not going to increase their size, but I am going to bold them. Now, going through all of these formatting techniques here, you will really only have to do this once. Once you've created a data table like this, you can then just copy and paste that data table into any other experiment that you're doing. The format will basically be the same. You will have an independent variable that will have a delta C and a total uncertainty, and of course a delta R, and then you'll have a dependent variable that will have these columns. You know, these things will really not change. The processing information might change, so of course you won't have a t-squared or a squared column in every single thing you're doing. But in this data table, I'm trying to include all those various options so you know how to do everything. But the basic bones of it, you can just copy and paste from this point on. So it's worth making a good job of the first one. So now, of course, when we square our t, we will have an uncertainty in t squared. So that would be delta t squared. And just now that I've sorted out all that formatting, I just go and copy that t squared symbol and pop it in there. Something about pasting in spreadsheets, so you can paste in lots of different ways. You can paste formulas, you can paste formatting only without the values, you can paste things without their border formatting. So if you go and copy something but you only actually want either the formula but not the actual answer, if you want the formatting but not the actual numbers, you have all those paste options. So go and edit and paste special, and you've got loads of different options to play with. So then finally, we will have our 4 pi squared L column. You should never ever put data into your graph that you haven't already fully explicitly said in your table. So here's our 4 pi squared column. I'm going to get my pi symbol from my Google Docs. It's a special character. I'm going to paste it in. But then I remember, it's pi squared. So I need to go and get one of those superscript, subscript cells again. So I'm just going to take it from here. Something that already has been sorted into superscript. Pop it in there and then replace the t with pi. So just a whole bunch of Control C, Control V going on here, folks. And there we go, 4 pi squared. And the only thing there with a unit is L, so the unit is meters. And because the only measurement in there is L, the uncertainty in that 4 pi squared L will be the proportional uncertainty from our length measurement. And the easiest way to pop that down is, of course, our percentage uncertainty. So then I go back and think about which other parts of my table might benefit from expressing a percentage uncertainty. So because I'm going to do the uncertainty in t squared, I'm going to want to know the percentage uncertainty in t so that I can double it. So I add in a column for my delta t squared. You see I'm using just the little grab function there. So when I click on a column and I pop my mouse to the top of it, when the little hand appears, it means I can drag that anywhere. And you can do that with the whole thing. So I could highlight this whole table and drag it anywhere I wanted. It's quite a handy little thing to be able to do. So there I've got my percentage delta t in there. I'm just going to do a little bit of formatting and make sure these look like the rest of my table. So while I dot around here quickly and sort out this formatting, this would be another good opportunity for you to pause the video and get your table up to this point, because we are about to start populating it and learn how to put in all of our formulas. So this is pretty much the final table format that we are going to populate. You don't want to copy and paste this yet though to your other experiments, because we're going to fill it with formulas, and that means you can copy and paste all of those in the future and you don't have to put them in from scratch either. So let's get started with putting our data in and seeing how we can process it in spreadsheets so much quicker than we can manually. So I'm going to start popping in my length values here. See how I notice how I try to type it in to 4 sig figs, which is what my reading uncertainty allows, but then it snaps back to only being the sig figs, so the numbers without the zeros. So don't worry, I can sort that. I'm going to highlight it, click on my blue square and drag down. The spreadsheet recognises the pattern and populates the rest of the numbers. Particularly good if you have a list of loads and loads. And then I can use this increase my decimal places button and bring those sig figs back up to match my uncertainty. So my uncertainty is to 3 decimal places, so that is what my data has to be to. This was using a meter stick, I assume, so I go and look up the calibration uncertainty for my meter stick and pop it in here. So we go to our standard calibration data, and a wooden meter stick has a calibration uncertainty of 0.5 millimeters. So that is what I put into my calibration uncertainty column. In this situation, every single calibration uncertainty will be the same for all of my lengths because I'm using the same measurement device. In digital measurement devices, we often get that, of course, that calibration uncertainty of 0.5% of the actual reading, and we'll see that a little later on for our period measurements. So because it's all the same for all of my data, I can click on the cell and drag that blue square down, that little blue square in the bottom right, and it will populate it for the rest. And here comes the first of my formulas. So I'm going to use my single unit combination formula, so that's square root of delta r squared plus delta c squared. And I can put that into my spreadsheet. So I press equals to tell the spreadsheet to do a calculation for me. For a square root, you literally just start typing square root, and the spreadsheet, I spelled it wrong there, the spreadsheet will recognise it for you. There we go. You click on, you actually have to select that option. So then I go and click on the, well for this, the value of my delta r is actually going to stay the same for the whole time. So I'm literally just going to type that in, which is 0.005. Before I do though, I'm just going to add a little extra bracket because we want to square root an addition. So first of all, I'm going to pop in my 0.005 and square that number. And then I'll close that bracket, and to say squared, I just use the little angled top hat symbol and to the power of 2. Sorry, and then close the bracket. So I put a square root, I've opened the bracket for all of my addition, I've put the 0.005 squared into its own bracket. I'm now selecting the delta C number from its cell, squaring it, closing that bracket, and then closing the brackets for the whole square root. Just like typing it into your calculator, folks. Okay, and then it's given me a number. I click on that, drag the little blue square down for the rest, and it will apply the same to the rest of my rows. Now, as we can see here, guys, it's given it to way too many sig figs. So while they're all highlighted, I'm going to use the reduce decimal places button and bring it down. And of course, this always means that your rounding is completely reliable. I'm not sure why when you go through these formulas and put in the stuff that it gets rid of your border editing. If you know why, please let me know. So at this point, guys, just pause the video, go and copy the data that I've linked in the description and paste it into your own sheet so that it looks like this one right here. So we're going to calculate our mean now. So we're going to press equals to tell the spreadsheet that we wanted to do a calculation. And we just start typing the word average. And it's usually the first option that comes up. It's just this bog standard average one we want. We go ahead and we highlight the row of data we would like it to take an average of. and press enter. My spreadsheet did it automatically here because Google learns what you want. So I'm going to try and do it again so that it does it from scratch. So here we go. So there's the average option. Click it, it opens a bracket for you. You go and highlight the row of data you would like it to average, close the bracket and press enter. And you can see Google has also learned that I want this to 2 decimal places, but if yours isn't, then please reduce your decimal places. Highlight them, click on the box and drag down. You should only have to do it for one cell before you click on the box and drag down. It will then apply that calculation correctly to every single other row. Okay, and again, if your decimal places are now not matching the raw data, you need to go and change them using these buttons up here. So we're going to do our calibration uncertainty. I did not know the calibration uncertainty of this device, so I'm going to carry out the 0.5% plus 1 digit one because it's the hardest version and I'd like to show you how to do it here. So again, starting with equals. So I'm just going to make a little mistake here. We'll just wait for me to get over that. And another one. So yeah, here we go. So 0.5%. So 0.5 divided by 100 multiplied by the cell. So click on the cell so that it will apply this to each cell as you drag down. You don't want to type in the number, otherwise it'll do it for 2.01 for all the others. But we don't want that. We want it to apply individually for the cell. Close that bracket and then add your reading uncertainty on at the end, plus 0.01. So we've just said 0.5% of the number in that cell plus 0.01. Click and drag that little blue square down and then go up to our reduce our decimal places. What am I up to? I'm just double checking. I'm just showing you that it's applied it to each individual cell. So if I go into I6, it's applied it to I6. Okay, now I go and highlight it and reduce my decimal places. If they were different to begin with, first of all, it will make them all the same and then it will bring them all down together. Lovely, and there we go. And though that calibration uncertainty is of the same order of magnitude as our reading uncertainty, which is a nice indication that we're going along the right lines. And I think at this point is I've just realised I've forgotten my random uncertainty column. Only took me almost the entire table. So here we go, let's do our delta U column. Now I will warn you folks, the formula I used to come up with this, to do this, I did not come up with myself. A pupil had to kind of highlight to me the best way to do it. So you're going to see a later version of the table now as it switches to it, where I went back and put it in. So you're going to get a little preview now of how small our table is going to end up being, which I hope you like. So for our random uncertainty, we're going to press equals. Then we're going to open up a bracket and start typing the word max. And select the max function and it will find for you the maximum number within your 5 repeats. Close that little bracket, say minus, and then obviously enough, start typing min. Select the function, go and highlight the same set of data. So your first row of repeats, make sure not to highlight your mean. Close your bracket, close the overall brackets and then say divided by 5. And there's your random uncertainty, folks. We click on it, we drag that square button down and it will apply that to every other row. And there are your collect random uncertainties. As you can see, guys, this is not the first time I've done this in these cells. So they're already at the correct number of decimal places. Please reduce your answer to give you only a single sig fig. So the screen's now going to pop back to my earlier version and these numbers will be in. And the first two are actually slightly incorrect there. You see there's 0.01, but the actual uncertainty was 0.008. So it's always a good idea just to increase the decimal place, use the increasing decimal places button on your spreadsheets just to check that it hasn't rounded too harshly for you. We want to make sure our uncertainties definitely go to that first sig fig. Okay, so it doesn't hurt just to click on it and increase the decimal places just to check that the one you're seeing really was the first one, because that should be 0.008. Okay, so it's time to combine these three uncertainties. So again, we are using the same unit combination formula. So I'm going to open a square root by pressing equals and typing start typing square root in and selecting the square root function. I'm opening a bracket to contain everything I want to square root, and then my second bracket is containing just the reading uncertainty 0.01 squared. I close that one. I open the next one for my delta u, click the cell, tell it to go to the power of 2. And I think I choose to pop that back inside the bracket. I don't think it actually matters whether if your power of 2 is outside or inside, but I think I go back and put it inside. Yes, I do. Add your delta C, open a bracket, go select the cell, don't type the number. I'm only typing the reading uncertainty one because it's exactly the same for every single one. Close it, close the bracket for that, and close the overall bracket for the square root. And there we go. Click on it, drag my blue square down. Loads of sig figs, so let's bring them down. Lovely. And now we're going to change that delta t uncertainty into a percentage to make it easier to get our t squared percent uncertainty. Just obsessively fixing my border here. Okay, so just like you would in your calculator, little, so delta t, click the cell, divided by slash mean t, and then you don't have to times by 100 because you press enter and then go and tell the spreadsheet it is a percent, and it will put them into percent for you. We're going to reduce the sig figs and drag it down. Now I've got 2 there that start with a 1, so I'm going to allow them to stay as 2 sig figs, and the other 3 are just a single sig figs. And so we're going up to t squared now. So we press equals, we go and select our mean t, cell, not type the number, and to the power of 2. Simple as that. Click it, drag that blue square down, and reduce our sig figs to match our mean. And of course matching our raw data, which is 3. Our percentage uncertainty now, so if it's percentage uncertainty in something that's squared, then that is double the percentage uncertainty. So just checking off all my sig figs there. My bottom 2 numbers have 4 sig figs, so I need to individually reduce those so that all of my process data is never greater than the sig figs of my raw data. So I'm going to press equals, go and select my percentage delta t, and then just times it by 2. I'm going to tell the spreadsheet that this is a percentage again. And that is indeed double that, and drag my blue square down. And I'm going to reduce my sig figs. So these top 2 need to go down to 1, but the others are all a 1 point something, so they can stay with their second sig fig. So finally, our 4 pi squared times L column. So I literally type in 4 pi squared times something, so 4 times. Now you type the word pi, pi, and it's an actual function. So it just says, would you like the number pi? And you say yes. We're not actually doing much with it, so we're just going to close that bracket. And then we're going to say to the power of 2. That bracket is looking for it to a certain number of sig figs. I believe. And then we just say times by, and we go and click the L cell, so the top one, and press enter. That is 4 pi squared times L. Drag it down, reduce to our raw data sig figs. So what I'm just thinking about here is the fact that, of course, my length data is to 4 sig figs. So I can keep that, because this is a length thing, I can keep it to 4. I've had to reduce that 118 one to another smaller number of decimal places to keep it to 4 sig figs. So my percentage delta L, final formula of the day, we're going to press equals, we go and press our delta L. Okay, we divide it by our L. Click on it, tell the spreadsheet, please give me this in a percent, and drag down. And I'm reducing all the ones that are not 0.1 into a single sig fig, and repairing my borders. Oh no, it's gone wrong. Oh, it's a disaster. Excuse me for a second, folks, while I fix this. So this is a pretty massive table. Not all of your tables need to be this big, not all of them will need this much processed data, but it is pretty massive, and we want to be able to fit it onto printing out of an A4 piece of paper. So it's time to go and fix the widths of those columns. So we're now going to go along, and for every column we're going to double click. When that little blue arrow appears at the top, double-edged arrow, we're going to double click, and those columns are all going to reduce themselves to their minimum possible size for what you have put into them. I don't know why this first repetition column wouldn't go any smaller, but I just fake it. There we go. So double clicking as we go along, and our very large table maintains all of its detail, becomes a lot more compact. And now that is a table that we can easily fit onto an A4 document as part of our write-up. When we're writing up our investigations, I would always encourage people to put these in as part of their Google Doc. Google Doc and Google Sheets work really, really well together. So there we go. There is our completed table with everything in it. A marker would be able to look at everything here, follow a single line of data all the way along horizontally, and check that you've got the correct numbers. You would always show a single, for example, your top number for length of 1 meter there. Below this table, you could show a full set of calculations to show how you got each of these uncertainty numbers, but you only have to show those set of calculations for one set of data, not for them all. At this point, we now have a data table that you can copy and paste for any other experiment. It's got all of your uncertainty formulas already inputted. It's got lots of common processing formulas inputted. So I would use this as your basic template for any other data table that you were doing, and just delete the columns you don't need. I'd probably recommend that you guys take a break at this point, pause the video. You know, this has been a long process, but I'm going to go straight ahead and make the graph, and so please come back and join me whenever you feel ready. So to make a graph on a spreadsheet, there is a first initial thing that you can do to make sure you are going to get the right values onto the right axes. Two problems can come when you make a graph. If you highlight both your X value columns and your Y value columns together, first of all, they can go onto the graph the wrong way around, and second of all, they can produce two separate graphs. So my advice to you is highlight only your Y-axis numbers. So here I've done that, only my Y-axis numbers, 4 pi squared times L, insert chart, and there we go. So obviously I don't have an X-axis right now. Google has learned that I always want a scatter chart, and it will learn from you as well as the more you do it, but if not, just for chart type, just go down to scatter. It's always the one that you want for physics. And we're going to go to add X-axis. So click on Add X-axis, just moving this out of the way so it doesn't cover any of my table. And then click on this little grid symbol, which allows you to highlight the numbers rather than type them in. So we're going to go and highlight our x-axis, which is just the t-squared column. There we go. And there is our graph. So there's a number of aspects of this graph that we have to fix to make it advanced higher quality, but it's pretty easy to do, particularly in Google Sheets. So I'm going to delete this title. It's unnecessary to have a title in a physics graph really, and also it's wrong. Be aware guys that in your advanced higher investigations, you really want your graphs to be of A4 size each. So once you finish your graph, you probably want to copy and paste it into a separate tab so that it can be A4 size. So we're going to go into customize, and I just like to start from the bottom. So I'm going to go down to grid lines. And the first thing I'm going to do is put all my grid line counts up to 10, so major and minor, for the vertical axis and the horizontal axis. And now it looks like graph paper. There's a problem now that my data points are larger than those boxes, but we'll fix that. Next thing I'm going to do is force all my minimum values on my axes to be 0. There we go. And now I've got a very nice directly proportional relationship. So in horizontal axis and vertical axis, make your minimum values 0. We don't tend to have a legend, so there's not really much to do in there. In series, that's where we can control what our data points look like. So we do not really want our data, we have to have our data points to be smaller than an individual little box. So we really need to kind of put that right down. So you can either do a cross mark. I wish they had crosses like plus crosses, but they have the X's. So the X's make for a better, more precise point than the dots really. And I find size 3 for the X marks works really, really well. But you can also use size 2 for the circular points if you really want to. I'm really not sure why I haven't reduced my size points. Usually I must have got distracted here folks, I'm really sorry. So that's 7px, I would exchange that for a 2 or a 3. 3 for the X mark, and if you really want to have a circular point, a 2 works well. So in this series section is also where you'll get your trend line. So if you just scroll down a little, never forget to scroll down, there's always so much more there. We can click trend line. I like to change my colour, the colour of mine, just to make it look a little bit different. And we can also, this is also where we can see our equation. Now it does have an error bar option there folks. I would like to say at this point that there aren't actually specific uncertainty marks for error bars. So although it's nice to add them, you do not need to. You do not need to add error bars to your graph to get full marks for your graph, full mark for your uncertainties. So I'm not going to bother talking about them today. So what I've got there, folks, is my equation of my straight line, and I've also got something called my r-squared value. Now the r-squared value describes how varied the points were. So you can see my r-squared here is 1, and that means that every single one of my line of best fit runs through every single one of my points. If my points were a little bit more scattered, and my line of best fit had to make a choice and miss a few of them, my r-squared value might go down to 0.97 or 0.96. So it's a number that describes how close your points were to your line. So just go and have a click around in series and get everything onto your graph that you want. We now don't want a chart title, but we do want labels for our horizontal and our vertical axes. So our horizontal axis is t squared in the units of s squared. So I'm just going to click over here and highlight those. For some reason I highlight them separately. Who knows what's going on? There we go. And I go back very inefficiently and go and get my s squared. But it's good to know you can copy and paste things. Anything from your titles in your table, you can just copy and paste in as your labels. So there's my horizontal label, and my y-axis label has already gone in correctly. And there we go. That is a graph that is at advanced higher standards. So like I said, the only other thing you'd want to do, folks, is perhaps paste that into a new tab and make it A4 size. So make it the size of a whole page. And I do make mistakes, folks. I am only human, but here I am going back and catching that too large data point. So I do choose to keep them as circles here, but I'm going to make them very small circles. So I think, yeah, down to 2. Try out 3. So it's important, folks, that, that your data point fits within a single box. That is what your marker will be checking for. If it doesn't, you will lose the mark for getting your data points correct on your graph. So even though you're thinking, oh, my spreadsheet has made my graph for me, of course my data points will be correct. If the actual marks are not smaller than individual boxes, you will lose that mark. So now we are going to find the LINEST data. So you've done a little bit of this, if you've done a little bit of this before, this is to find your actual gradient and intercept. The gradient is pretty much always the thing we want from a straight line graph. So we press equals and we start typing LINEST. Now Google Sheets leads you through it. We just highlight our y-axis values and press comma, not close the bracket. There we go. Then we press comma, space, highlight our x-axis values. Comma, space. We're going to type true, which says we would like it to calculate our intercept. Comma, space, true for the final, close brackets, press enter. And we get all these numbers. Okay, now I'll be honest with you folks, I don't know what all of them are, but we are only interested in 5 of them. So I'm just going to move some things around on here a bit because at the moment my numbers are beholden to the widths of my columns that I controlled earlier for my table. So I think I noticed that in a second and I drag them around. The top left number is the gradient. The one below it is your uncertainty in that gradient. The number on the top right is your intercept, which we usually call C, and the number below that is delta C. Below that on the left is your R squared value in a lot more detail. And now I notice, oh, these things are really, really squished and I drag them around. So guys, if you have included delta R's, delta C's and delta U's in your data table, you will qualify for the first of the 3 uncertainty marks. If you have successfully combined those uncertainties in your data table, you will have the second of the 3 marks. LINEST, carrying out a LINEST analysis on your straight line graph and taking the uncertainty in your gradient from that is going to get you that 3rd and final uncertainty mark, and doing this consistently through your investigation, obviously. But the major issue that people usually have when they take this data is that they forget all about the sig figs. So all of a sudden you've got data to masses of sig figs and you really want to take it all. You feel that, you know, more numbers is better. But as always, you cannot do this. So you will lose all the marks for using LINEST, all that credit for going through this relatively complex procedure. You will lose that if you then do not pay attention to your sig figs. So our raw data is to 3 sig figs, that's the minimum number of sig figs. So therefore our gradient is restricted to that. Okay, so I'm going to rewrite the values just below. And I would really recommend that you do this in your own write-ups. You show your full LINEST data, so copy and paste the full LINEST with all of its sig figs, and then just below it, show how you're going to round it off correctly. So if I round my gradient here to 3 sig figs, I get 9.81. If I round my uncertainty to the first sig fig, I get 0.06, and those decimal places are the same, so brilliant, don't have to go any further there. My intercept is, I'm just going to put it below, I think, is minus 0.0652. I think this is me just thinking about my sig figs here. Well, why have I done that? Oh, I've done that because my uncertainty to a single significant figure is 0.6. And so that means because my uncertainty is to 1 decimal place, my data has to be to 1 decimal place. And so I've rounded my my intercept to 0.1, getting ahead of myself a little there. So those numbers, those 4 numbers that you can see I've just done, those would be the ones that I use going ahead. If I do a calculation with my gradient or I state my g-value, the number I state is 9.81. I cannot use all those other sig figs. I do not have access to them. And there we go, folks. That is digital tables and graphs to advanced higher level. If you've been going along with me during this tutorial, I know it's been long, but if you've been going along with me, you now have a table that you can copy and paste with all of its formulas and use from that point on, which is fantastically useful. Okay, I guarantee you this table has everything in it that that you need at this level, and I think is the best way of laying one out. So I am just showing you now that you can copy and paste the table, and everything will come with it. And if I then delete some of my data, so say I deleted my raw data, so that's up to those columns there. And there we go. Then my my calculations will go away. But if I then all of a sudden populate it with a new set of data, those calculations are just waiting for numbers to be there. So I can now paste this table into whatever experiment I'm doing. For example, the measuring G experiment, which I'm about to ask you to do in our next video at home. A different kind of measuring G. And if I populate it with data, here we go, then all of a sudden all of those calculations are valid again. So I hope you found this useful. I hope you've learned a skill for life today, and I'll see you in our next video where I'm going to get you to use all of these skills in a brand new experiment that you guys are going to do by yourselves. Thanks, folks.